Hi, this is Geometry Review 2. I hope to cover circles and quadrilaterals. If I can also complete solid geometry, I'll try. Otherwise, there'll be a review 3 for solid geometry. Moving on, circles. So, circle area is pi r square, circumference is 2 pi r, yeah, and sometimes they call it the diameter into pi because the diameter is 2r, yeah. And well, let's talk about an arc. Okay, so this blue portion out here, that is this part of the circle which is blue, is called an arc. Okay, and if I say that the arc is 60 degrees, yes, then it simply means that this being the center O, yeah, forms an angle of 60 degrees when you have the two radii touching the arc. In other words, the arc which is 60 degrees subtends an angle at the center which is 60 degrees. Okay. Now, this red portion is called sector. So, in a circle, the area of the sector is theta, that is degrees, upon 360 into pi r square. And the length of the arc is theta over 360 into 2 pi r. So arc is a part of the circumference and the sector is a part of the area. Okay, now, since the arc subtends an angle of 60 degrees at the center, then from those 2 points, endpoints of the arc, the angle subtended by the arc on the circumference is always half of the angle subtended at the center. It's a rule. And you can extend it to major arc and minor arc. So for example, if I were to say that this angle was 60 degrees, then this angle out here would be 300 degrees, right? So therefore, my arc would be this blue color portion. It's called the major arc. There's a minor arc. The minor arc, which you saw in the previous screen, was 60 degrees, and the major arc is 300 degrees. And so by that property that we discussed, that if the arc subtends an angle at the center, which is 300, then that same arc length subtends an angle which is half from this point, and that would be therefore 150 degrees. Yeah. Okay. So I'll just draw it quickly out here, what was drawn on the previous screen. So you can compare it. So you could say that this is one of the important properties of circles. Okay, right. The next property of a circle is that if you have a circle and if diameter is the hypotenuse for a triangle which is inscribed in the semicircle, so diameter divides the circle into two parts. All right. And if it forms, it can form multiple right triangles. For example, even this one out here is a right triangle. As long as the diameter is the hypotenuse, yeah, then it will form a right triangle as long as the vertices touch the circle. So these are the vertices. Yes. So as long as the vertices touch the circle, and if the hypotenuse is the diameter, then it will form a right triangle within the semicircle. And it is just an extension of the earlier point or the earlier property that this angle out here is 180 degrees, which is basically the arc. This, if you consider this red portion as the arc, yes, which is subtending an angle of 180 degrees at the center, then from that endpoints of the arc, anywhere on the circumference, it will be half of 180, which is 90 degrees. This and this, 90 degrees. Okay. All right. Now, let me see if I've got a circle. Yeah, I've got a circle. So let's consider a circle. Yeah. And now let me see if I can draw a quadrilateral within the circle. Okay. So any quadrilateral, it could be a rectangle, square, any shape, any four-sided polygon inscribed in the circle is called a cyclic quadrilateral. So remember the term cyclic quadrilateral. So the property is that cyclic quadrilaterals, opposite angles, they add up to 180 degrees. As long as the vertices are touching the circle inside. Understood? So that's another property. Yeah. And I don't know if you can figure out, but these properties, they kind of are an extension of the first property about the arc subtended an angle at the center and that same arc subtending an angle on the circumference. Yeah. So it is kind of an extension of that in a way. Yes. So that's the second property. Yeah. Now, I can't recall anything more about the circle other than these few properties. Yeah. So let's jump into some examples. Yeah. So if I have a circle and then a square or any, let's say a square. Yeah. Let's say a square. Yeah. Okay. And then within the square, I have another circle. So imagine this is touching yeah, it is touching. Okay. So if you have a circle and then a square and a circle inscribed in it, then what kind of relationship can you think is taking place out here between the outer circle and inner circle? Let's figure that out. So let's assume that we are trying to figure out the ratio of the outer circle area to the inner circle area. And what is given is that given is side of the square is 5 centimeters. Okay. So now we have to find out the ratio of the outer circle area to the inner circle area. Given is the side of the square is 5 centimeters. So actually the number is not important. One could figure out without the side of the square. But let's figure it out with a number. So if the side of the square is 5 centimeters, that means this is 5 centimeters. I'll use a different color. So this is 5 centimeters side length of the square, which means that the diameter of the inner circle is 5 centimeters, which means that the inner radius is 2.5 centimeters, and therefore the area of the inner circle is pi times 2.5 square, and 2.5 square is 25 square, 625, and 2.5 square would be 6.25 pi centimeter square. Now, the diagonal of the square, yeah, that is this portion. If the side of the square is 5, then the diagonal is 5 times root 2, based on the isosceles right triangle property. If you remember 5, 5, 5 root 2. So then we know that the diameter of the outer of the outer circle will be 5 root 2, because the diagonal of the square, yeah, so diameter is equal to the diagonal of square, which is 5 root 2. Now therefore the outer circle radius, the outer radius is 5 root 2 by 2, which can be written down as 5 upon root 2. That simplifies to this. So just the breakup, root 2 times root 2, for those who do not know, is 2. So this 2 can be written as root 2 and root 2, 1 root 2 and 1 root 2 in the denominator and numerator cancel. So you have 5 by root 2 as the radius. And therefore the outer area, outer circle area, is pi times that 25 by 2, which is 12.5 pi. And so what we realize is that 6.25 is half of 12.5. Therefore, the ratio of the outer circle area to the inner circle area is 2:1. And so this is given. This you have to take it for granted, basically, that you don't have to really solve it. Just remember it as a property. So if there's a circle, then a square, and then a circle, then the outer circle area to the inner circle area is always twice of the inner circle area. Okay? Yeah. So I'm not going to get into the proving part of it. You can simply use uh, variables instead of numbers and solve it. Yeah. Similarly, let's say you have a square. You have a square. And then you have a circle inside. And then you have, you know, a square inside. Yeah. So again, assume that the radius of the circle, so we have to find out, question is find the ratio of the r square, or you can say the big square versus the small square. So out here, r square area to inner square area. Yeah. Given a radius is for 5 centimeters. Okay. So if the radius is 5 centimeters of the circle, then clearly we know that the diameter of the circle is 10 centimeters. Correct? That's the diameter. And that diameter is also equal to the diagonal of the square, of the inner square. Right? Yes. It's also equal to the side of the outer square. Isn't it funny how things are related? So this diagonal of the inner square, yes, which is the diameter of the circle, yes, and the diameter of the circle can also be considered at the side of the outer square. So you can say the outer area, yeah, is 100 centimeter square, and the inner area. So then we know that if the diagonal is 10 centimeters for the inner square, then the inner side is equal to 10 by root 2. Again, we are using the right isosceles triangle property, side root 2, right? Yeah. So the calculation part, I'll just do it out here. So we know it is x is to x, that is 45, 45, and 90, x times root 2. So we know that x is 10. I'm sorry. The diagonal is x root 2. So x root 2 is 10. Yes, that's the diagonal of the inner square. Then x is 10 by root 2, and that's how I got this. Or you can use the full Pythagoras theorem and get your answer. So remember the shortcut. So 10 by root 2 is the inner side. Therefore, the area is 100 by 2. Yeah, which is 50 centimeters square. And again, you have the same part, 2 is to 1. The outer area of the square is twice the inner area of the square. So remember these properties: circle, circle, or square, circle, square. They should be touching, right? Okay. Um, right. So that's about the circles. Yeah. Okay. Um, let's move on to quadrilaterals. If I do remember any property of a circle that I've missed out, then I'll discuss it in between. Otherwise, let's move on to quadrilaterals. Okay. So 4 main quadrilaterals which are dependent on each other in some way. So let's first consider parallelogram. Yeah. Now, parallelogram, it looks like this. Mm, like this. Let me use straight lines. That's a parallelogram. So the properties of parallelogram. First property. First, I'll write down the area is base times height. Okay. And in a parallelogram, so let me extend this parallelogram. Let's see if I can do that. Wait a minute. I'll just erase this parallelogram because I want to extend it. Yeah. Okay. So that's my parallelogram. Yeah. So out here, opposite sides are equal and parallel. That's the first property. Yeah. Opposite sides are equal and parallel. So if this is x centimeters, then this is also x centimeters. And if this is y centimeters, then that is also y centimeters. That's how I meant it. Okay. Then next, the diagonals are not equal. Yes. Usually the case. Okay. Because when the diagonals become equal, then it will no longer form a parallelogram. I think it will form a rectangle, but the diagonals are not equal, and diagonals bisect the angle at the vertex. What does that mean? It means that suppose this is my diagonal, then it will bisect the angle at the vertex. Yeah. This angle, these two are equal. Yeah. Difficult to believe because the top right one doesn't look equal. That's because of my drawing. But usually they don't appear to be looking equal, but they're actually equal. The diagonal bisects the angle at the vertex. Okay. So this leads me to another important point, that the opposite angles are equal, which means that if this is 60 degrees, then this is also 60 degrees. Got it? Yeah. And similarly, my other diagonal will also bisect the angle at the vertex. So you might be wondering why I'm drawing two angle lines, because uh, I just want to show the difference in the two opposite angles, that not all angles are equal. So that's the reason I'm drawing two angle lines. Otherwise, it might seem that all four angles are equal, which is not the case. Okay, so the opposite angles are equal. And another important point is that the diagonals bisect each other. Diagonals bisect each other. What does that mean? It means that these two sides are equal, and so is this and this side. And because of this uniqueness of the parallelogram, the four triangles formed owing to diagonals bisecting each other are equal in area. Are equal in area. So what is equal in area? The four triangles formed are equal in area. Okay. So the four triangles formed are equal in area. Okay. So remember the properties of parallelogram, because the parallelogram is like the, you could say, the base um, um, quadrilateral. Yeah. Based on the parallelogram, you have a rectangle formed. Based on the parallelogram, you have a square formed. Based on the parallelogram, you have the rhombus formed. Okay, so parallelogram is like the base, and from which you have the rectangle, from which you have the square, and from which you have the rhombus. Like for example, in a parallelogram, if I were to say that, the diagonals are equal, yeah, then if that was true, then it would become a rectangle. And in a parallelogram, if I were to say that the diagonals are equal, the sides are equal, then it would form a square, right? And what do you think would happen to the parallelogram if it were to become a rhombus? One simple thing, that the diagonals should not only bisect each other, but they should be perpendicular bisectors, and it would form a rhombus. So let's discuss the rectangle now. So rectangle, very simple. Yeah, that's a rectangle. And you have the diagonals which are equal. Yes. And we know that in a rectangle, yeah, all the angles are 90 degrees. So we'll begin with area first. Yeah. So what's the area? Base times height. So again, see, it's all developed from the parallelogram. So base out here is the length, and the height out here is the width. So that's your L and that's your W. And all angles are 90 degrees. So now if you see, unlike the parallelogram, the diagonals are equal, right? Unlike the parallelogram, diagonals do not bisect the angles at the vertex, meaning the 90 degrees is not equally divided by the diagonal. But like the parallelogram, so now like the parallelogram, I'll put it in blue. Like the parallelogram, yeah, the diagonals bisect each other. Diagonals bisect each other. Yeah. The sides, opposite sides, opposite sides are equal and parallel. Got it? Opposite sides are equal and parallel. Okay. Yes. Again, the four triangles formed are equal in area, just like a parallelogram. So all of these triangles are equal in area. Strange but true. Strange but true. Hang on. Huh? Okay, so that's about the rectangle. Yeah. But before I move on to square or rhombus, I want to ask you a question. Okay. So let's take an example. So let's consider a parallelogram. Okay. So that's a parallelogram. Okay. And mm, we have a rectangle. Yeah. We have a rectangle. So if I were to give you the dimensions as 8 centimeters, 6 centimeters, 8 centimeters, 6 centimeters, right? Can you tell me which one is bigger? Is the rectangle area bigger or the parallelogram area bigger? Okay. One is a rectangle, one is a parallelogram. Which one has a greater area? The answer is simple. It's the rectangle which will have a greater area. So the area of the rectangle is L into W, which is 8 into 6, 48. And out here, how we show that the parallelogram has area smaller than that of a rectangle, yeah, is simply by showing that this right triangle has a hypotenuse which is 6 centimeters, yeah, and we know therefore in a right triangle the hypotenuse is the largest length, and therefore the height h is going to be lesser than 6 centimeters. So out here base, the area is base times height, and the base is 8, but the height is lesser than 6. Therefore, the answer will be lesser than 48 centimeters square. Understood? And therefore, we can say that the area of the rectangle is bigger than the area of the parallelogram, given the dimensions 8 and 6 for both of them. Right. Let's move on to square. Square. So I don't need to really discuss all the points out here. Basically, everything's equal. You name it and it's equal. Sides equal. Angles equal. Diagonals equal. Diagonals bisect each other. At 90 degrees. In other words, perpendicular bisectors. Triangles formed are equal in area and identical. The four triangles formed are identical. Look at this. First, it forms first the diagonal separates, divides the square in two equal halves, or you can say two isosceles right triangles, and then further when you add another diagonal, then it forms four triangles, and those four triangles are equal and identical. So equal in area and identical. And they're perpendicular bisectors. So they're perpendicular bisectors. The diagonals are perpendicular bisectors. The diagonals bisect each other at 90 degrees. Diagonals are equal. Angles equal. Sides equal. The diagonals bisect each other at 90 degrees. The diagonals bisect the angles. Diagonals bisect the angle at the vertex. So this is from the parallelogram. This is from the parallelogram, at least the equal in area part. Diagonals are equal. This is similar to rectangle, but not parallelogram. Okay. Angles equal. Same thing as rectangle, but not parallelogram. Sides equal. No. Sides equal. This is only for square and rhombus. Okay. But as you can see, the properties they come off from, yeah. So out here they bisect each other, but not at 90 degrees. So this also is sort of from the parallelogram, the bisecting each other part. Bisecting each other at 90 degrees, this is the rhombus part. So this part is for the rhombus. at 90 degrees part is for the rhombus. So we'll discuss rhombus. So out here, first of all, the area again is base times height. Yeah, which is nothing but you can say length into width, and because the length and width are equal, so you can say it's side square or simply length square, or you can say width square, whatever you want to call it. Yeah. Important part out here is that the diagonal is root 2 times the side. Is root 2 times the side. And because of this, we can also say that the area of a square is also diagonal square divided by 2. Very important property. Diagonal square divided by 2. Got it? Yeah, diagonal square divided by 2, which is nothing but side square. And finally, the rhombus. And I think with that, we'll end this video because I don't want to stretch it to 40 minutes. I want to keep it short. Okay. But we might do a couple of examples before I wind up. Rhombus. Now that is a rhombus. That's a rhombus. Yeah, that's a rhombus. So in a rhombus, you have the diagonals bisecting each other at 90 degrees, just like a square. In a rhombus, all sides are equal. All sides are equal, just like a square. And just like a parallelogram, it bisects the angle at the vertex. And as usual, the opposite angles are equal, like this. So as you can see, not all angles are equal, opposite angles are equal. So the points I want to make out here is, first of all, you could say the area is base times height. So if that is my base, B, then my height would be a perpendicular line like this. That would be my height to the base, perpendicular to the base. Got it? So that would be my height. Yeah. So the points I would like to make is all sides are equal. All sides are equal. Second point, diagonals are not equal. Remember, diagonals are equal in rectangle and square, not in parallelogram and rhombus. Diagonals are not equal. Diagonals are perpendicular bisectors. Are perpendicular bisectors, meaning they bisect each other at 90 degrees. Yeah. Then out here, the triangles formed, 4 triangles formed are equal in area. And just like a rectangle, yeah. In fact, I think just like a square, all the triangles formed are identical. True. Just like the square, all triangles are identical. Okay. Then opposite angles are equal. Equal. All sides are equal. Diagonals are not equal. Diagonals are perpendicular. By 4 triangles formed are equal, and opposite angles are equal. Okay. Yeah. And 4 triangles formed are equal in area and identical. Identical. So if you remember these properties logically, then you should not have trouble differentiating one from the other. Okay. Now, one interesting fact about the rhombus is that its area is half times diagonal 1 into the diagonal 2. So if you know the length of the diagonals, then simply the product and taking half of the product of the diagonals gives you the area of the rhombus. Okay, so you can sit down and prove it, yeah, by taking any, uh, I'll just show it to you if you want. Suppose if I take this rhombus out here, yeah, and suppose if I were to divide it into half like this, okay, yeah, and like this, okay. So now I'll consider the triangle ABC, no, triangle ABD. Triangle ABD, suppose if I say it is area of the triangle is half base times height, half base times height. Okay, so in triangle ABD, if I consider the base, which is BD, yeah, and the height as you can say half of AC, correct? Half of AC. Okay, so now I can say that this triangle ABD is also equal to triangle BCD. Yeah, triangle BCD is equal to triangle ABD is equal to half base times height. But in case of so basically I can say that half BD and half AC is for triangle ABD. Okay, so similarly, so triangle BCD, yeah, it'll be half. So let's call this half AC only if I want. Yeah, let's call it half AC. So it'll be half BD and half AC, correct? Yes, right. So if I were to add them up, then I'll get BD into AC. And what is BD? Diagonal 1. And what is AC? Diagonal 2. Correct. So then, why am I saying that the area is half times that? Why am I saying that the area is half times that? Because I made a mistake. It is 1/4 BD and 1/4 this one. This one is 1/4. This one is 1/4 plus 1/4. So here, this together, okay. So this is 1/4 BD into AC, and this is 1/4 BD into AC. And when I add them up, it becomes half BD into AC, and which is nothing but half product of the diagonals. Proved. Okay. Right. Moving on then. Now we'll just move on to some examples and wind up. So let's consider the first example. If I've got a rhombus and if I've got a square, yeah, okay. So remember, rhombus and square, all sides are equal. So let's say the side length of a rhombus and that of square, both are 5 centimeters. I'll put it out here, 5 centimeters, yeah, and the side length out here is 5 centimeters. Which one has a bigger area? So this one we know the area is 25 centimeters square. This one out here, how do you know? How do you know? Again, you use the same concept of base times height. Area is base times height, correct? So the base is 5 centimeters. That's my base. And the height, if I were to drop a perpendicular from here to here, so remember the perpendicular to the base, correct? Perpendicular to the base. That's my height, correct? So that's my height. And opposite 90 degrees is 5 centimeters. So that is my base, which is also the hypotenuse for this triangle. And so height is lesser than 5 centimeters. So my base is 5, but the height is lesser than 5. And therefore, it will be lesser than 25 centimeters square. Therefore, I know that If the rhombus and square is given to you and they both have side lengths 5 centimeters, then the area of the square is bigger than that of the rhombus. All right. Right. And that's it. I, yes, one example I would like to discuss based on a square. Yeah. Oh, yeah. And I would like to discuss trapezium also. So I would like to discuss trapezium as well. So first, let me cover trapezium before I move on to example of a square. Trapezium, British word, trapezoid, American word. But these days, they kind of use in both the text, American and British. So they interchange it. So that's my trapezium. Trapezium has only one pair of parallel sides. One pair of parallel sides. So just giving you different types of trapezium. Yeah, these are all trapeziums. All right. And what do they have common? They have one pair of parallel sides. And the area in a trapezium is average of the parallel sides, right? So if this is A centimeters and B centimeters, then the average is A plus B by 2 times the height. That's my area of the trapezium. Okay. So they also kind of use half sum of the parallel sides into height. So that's another way to look at it. Either you say average of the parallel sides into height or half sum of the parallel sides into height, same thing. One example on a square and then we wind up. I don't know. It's probably a long video, 45, 50-minute video. Square, square. So example of the square. Let's see. So that's a square. That's my diagonal. And that's, you could say this is my midpoint like that. Yeah, correct. Perfect. Right. So the question is, find the area of the red shaded portion given that this is the midpoint. Yeah, midpoint of, yeah, so this is the midpoint of AD, and this is the midpoint of AB. Got it? Yeah. So given AB is equal to, you could say 10 centimeters. Yeah, let's take it 10 centimeters, and it's a square. It's a square. Okay. Think about it. How will you solve it? So we'll do the mathematical way and then we'll use a shortcut. Okay. So method one. Method one. Yeah. So I know the side length is 10 centimeters. This is the midpoint. So therefore this is 5 centimeters and 5 centimeters. Yeah. Okay. And then what I'll do is area of the square is 100 centimeter square, right? Then half the area is 50 centimeter square. and which is the area of the isosceles right triangle. Okay, isosceles right triangle is 50 centimeters square. So from that, if I remove the area of this triangular portion, yeah, if I remove the area of this triangular portion, then I'll get the area of the shaded portion, right? So how do I know the area of the triangular portion? Very simple. It is a right triangle with side lengths 5 centimeter and 5 centimeter. So the area of, you could say, um, let's call this point M and N. So area of triangle AMN is equal to half 5 into 5, which is 25 base into height. So that's 12.5 centimeter square. And that I need to subtract from 50. And I've got myself 37.5 centimeter square as the area of the red shaded portion. Got it? Okay. Now, what I'm going to do is I'm going to use what we call um, yeah, hmm, correct. Okay. So I'm going to use symmetry to get to the area of the red shaded portion. So how do I use symmetry? Look at this. Um, Now I have got triangles out here. Okay. And if I were to use symmetry again, so basically I'm dividing the square vertically and horizontally like this. Yeah. So obviously, let me show it to you on a different page, because then this will get messed up. Okay. So I'll draw it again. So here it is. This was my diagram. Okay. Yeah. And I can have a similar diagram, I believe. No, I can't. Yeah, whatever. So I'll draw another diagram like this. So now this was the shaded portion out here in red. So if I'm using symmetry, which is basically to say that I am drawing another line like this, yes, and I'm drawing a vertical line like this, and then I'm drawing a horizontal line like this, correct? Then what you see is essentially 1, 2, 3, 4, 5, 6, 7, 8, 8 identical triangles. I know that the area of the square is 100, and I've got 8 identical triangles, correct? So therefore, 100 centimeter square divided by 8 gives me area of one one triangle. Yeah. And I need 3 triangles. So 100 by 8 is the area of one triangle multiplied by 3, and I've got my answer. So 3/8 of 100. 1/8 we know is 0.125. So 3/8 is 0.375 into 100, and that gives me the same answer as before, 37.5 centimeter square. So that is using symmetry, I've got the answer. And with that, I'll wind up my session. Thank you very much for staying tuned. As usual, I would like to let you know that all my videos, you better watch it from the playlist, which is there on this channel, Friendly Spider.
Okay, the playlist is named UGC CSR Net Part A videos. Thank you.